Hello, today we're going to be talking about reflection and transmission, a presentation by Christine Garcia and Jessica Gaitan. Reflection and transmission are the basis of ultrasound. Transmission is produced by sound waves that move through a medium, and those sound waves reflect back to the transducer during reflection. The sound waves are sent out from the transducer, and those waves strike its structure, and the waves are reflected back to the transducer in order to produce an image. Acoustic impedance is important when it comes to reflection and transmission, due to it being the resistance of sound traveling through a medium. Acoustic impedance influences the amount of reflection that is sent back to the transducer and how much of the sound wave is transmitted once it strikes tissue or a structure. Another important aspect in deciding how much sound is transmitted through a structure is attenuation, which is the weakening of sound waves as they propagate through a medium. As we can see in the images here, there is less resistance and more transmission in fluid structures like a cyst, because it has extremely low attenuation compared to a solid structure such as a stone, which has very high attenuation. In this demonstration, we can see how the light from the flashlight, which represents the sound wave from the transducer, is completely transmitted through the glass filled with fluid, representing a cystic structure. Like mentioned before, water has an extremely low attenuation as sound propagates through it. Therefore, the whole sound wave is transmitted and none of the sound is absorbed by the structure. In ultrasound, we can see this occurring with a cyst that shows posterior enhancement due to high transmission of sound. On the other hand, we can see that there is no transmission whatsoever with the stone, because solid stone-like structures have a very high attenuation and absorb the whole sound wave. We can see such examples in stones found in organs, such as the gallbladder. The attenuation creates a posterior shadowing since there is no further transmission of sound. Going back to attenuation, it is important to understand that three processes contribute to the weakening of sound waves as they propagate in a medium. These three processes decrease the intensity, power, and amplitude of the sound wave through reflection, scattering, and absorption. Reflection weakens the portion of the sound wave that continues moving in a forward direction. There are two types of reflection. The first one is specular reflection, which occurs when the sound waves from the transducer strike a smooth boundary and reflect directly back to the transducer in an organized manner. The second type of reflection is diffuse reflection, which occurs when the sound waves from the transducer strike in an irregular surface and reflect back in more than one direction. Scattering in ultrasound occurs when sound is redirected in many directions. Scattering happens when the diameter of the tissue is smaller than the wavelength. A unique form of scattering that takes place in ultrasound is called Rayleigh scattering, which happens when the diameter of the structure being scanned is way too small compared to the beam's wavelength. This type of scattering redirects the sound waves equally and uniformly in all directions. Rayleigh scattering is seen when the wavelength from the transducer strikes red blood cells due to their extremely small diameter in comparison to the wavelength. Absorption happens when ultrasonic energy is converted into another energy form such as heat. With absorption, higher frequency waves attenuate more than lower frequency waves. A good example of absorption in ultrasound is seen with bone, which undergoes extensive absorption. The angle that a sound wave strikes a boundary in between two different types of media determines the behavior of a pulse. The angle at which a sound wave approaches a boundary is the angle of incidence. The angle of incidence will tell us whether transmission, reflection, or refraction will happen. There are two types of incidence, which are normal incidence and oblique incidence. Other angles that relate to incidence are the angle of transmission, which is the angle at which the sound wave will continue to pass through the boundary, and the angle of reflection, which is the angle at which the sound wave will reflect back to the transducer after striking the boundary. Let's talk about the two types of incidence. The first one is normal incidence, which is when the sound wave strikes a boundary at a 90-degree angle. The sound wave is completely perpendicular to the boundary. The second type of incidence is oblique incidence, which is when the sound wave strikes a boundary at any angle other than 90 degrees. If a sound wave strikes a boundary at an angle that is less than 90 degrees, then the angle is an acute angle. If a sound wave strikes a boundary at an angle larger than 90 degrees, then it is an obtuse angle. Reflection and transmission occurs differently with each type of incidence. As mentioned before, normal incidence occurs when a sound beam strikes a tissue boundary at an exact 90-degree angle. When normal incidence takes place, reflection can only happen if the media on either side of the boundary have a different impedance. This difference in impedance in the tissue dictates what percentage of the incident beam is reflected. For example, if the two media have the same impedance, then no reflection will take place. Instead, all of the sound is transmitted. Secondly, if the impedance of each media is slightly different, then a small reflection will take place. And finally, if the impedance of the two media are largely different, then a large reflection will take place. As previously mentioned, oblique incidence occurs when the incident sound beam strikes the boundary at any angle other than 90 degrees. With oblique incidence, we cannot predict whether sound will reflect or transmit after striking a boundary. Oblique incidence does not follow the same rules as normal incidence does. With oblique incidence, reflections can still happen even when the impedance of the two media are exactly the same, or reflections may not happen at all even with different impedances. The same applies to transmission. When a sound wave beam strikes a boundary at an oblique angle, transmission may or may not happen. Two physical principles that always apply to reflection with oblique incidence are the conservation of energy and the reflection angle is equal to the incident angle. The law of conservation of energy tells us that the sum of the percentage of sound reflected and the percentage of sound transmitted must equal to 100%. The second principle states that the reflection angle equals the incident angle. When reflection takes place with oblique incidence, the sound beam does not reflect back to the transducer, but instead the beam is reflected in a different direction. The direction of the reflected echo is equal and opposite to the direction of the incident beam. Another thing that occurs with oblique incidence is refraction. If a sound beam strikes a boundary at an oblique angle, the transmission that takes place is unknown. But if transmission does occur, then the sound beam might travel straight ahead, or it might bend or change direction. And this is called refraction. Refraction is basically transmission with a bend. It's a change in direction of the wave as it travels from one medium to another. Refraction only takes place with oblique incidence and when two media have different propagation speeds. Snell's law lets us predict the direction of the refracted sound. It states that the magnitude of the refraction is directly proportional to the angle of incidence and the difference in velocity of the sound waves within the two tissue types. Snell's law describes the relationship between the angles and the velocities of the waves. The characteristics of each media impacts the direction of the refraction. Snell's law follows certain conditions when it comes to quantifying the angles of transmission and speed of refraction. Under these conditions, we identify medium 1 as the medium in which the sound is currently traveling, and medium 2 is the medium into which the sound is entering. The conditions of refraction tells us that refraction will not occur when the speeds of the two media are identical. The angles of incidence and transmission will be equal, and the beam travels straight ahead. The second condition tells us that if the speed of medium 2 is greater than the speed of medium 1, the transmission angle will be greater than the incident angle, and the last condition tells us that if the speed of medium 2 is less than the speed of medium 1, the transmission angle will be less than the incident angle. Thank you for watching. We hope you enjoy learning a little bit about reflection and transmission. Don't forget to like our video and subscribe to our YouTube channel.